All right, position, velocity, and acceleration. When we are going in this direction, we are taking the derivative, and when we are going in this direction, we are doing the antiderivative. Otherwise known as the indefinite integral. Okay? We get lots of problems dealing with the motion of a particle. Quite often the motion of the particle is in the x-axis. So that means we're only talking about left and right. So in our first example, interpreting the velocity function, I want you to graph our velocity function in y1. Right now, on Zoom 6 would be fine. Everyone's calculator is out. If everyone is putting this in their calculator. All right. So the SPT, remember S generally represents position. So the SPT would be velocity. Represents the particle moving along the horizontal, they're calling it the s-axis. From time 0 to 5, describe the motion. The first thing I want you to find is when that velocity equals 0 on your calculator. Oh, you cleared it. I would have answered, but you cleared it. Yeah, that's correct. All right, so now, find when that velocity equals 0. Equals what? Louder. 1.25. One more? Okay. 1.255. All right. So, and to the left of that 0 is my velocity function above or below the x-axis. It is below. We've got something that looks kind of like that. Yeah? Okay, thank you. All right, so if we're talking about motion in the x-axis, or horizontal motion, then what is it telling me from time 0 to time 1.25? Backwards would be to the left. So from 0 to 1.25, particles moving left. Because velocity is negative. Velocity is negative. And then from time 1.25 to 5, particle is moving to the right. Because velocity is velocity is a vector, so it has a magnitude and a direction. All right. Now this problem doesn't ask for this, but we're going to continue on. And I want you to find the acceleration function. We have our velocity function. How do we get to acceleration? Derivative. So help me. 2t.
8t
Plus, that would be for integral, right? I'm doing mean and we're doing derivatives again. So this is 8 times t plus 1 to the negative 2, correct?
plus 8 over 3 plus 1.
Careful, we bring this negative 2 down, we get 16, so it would be plus 16. Well, it's minus already.
Oh, yeah.
Yep. So plus 16 times t plus 1 to the negative 1, oh, sorry, negative 3. I'm doing it, t plus 1 to the negative 3. Okay? So there's our acceleration function. Now, in your y1 again, graph that and find the 0 or tell me about this function. One more time. Same unit, yep. there a zero? Nope. Tell me about the acceleration. Is it positive or negative in our interval? Positive everywhere. All right, so I'm making a little sign chart for velocity and acceleration. I know the velocity is 0 when time is 1.25. And to the left of that it was negative, and to the right of that it was positive. All right, and everywhere in the interval down here from 0 to 5, my acceleration was positive. Can you tell me now the interval for which this particle is speeding up? No. 1.25 to 5, and why?
It's all positive, so it's just faster, and then on the other side, it has to slow down and change direction.
Okay, so exactly it. Our velocity from 0 to 1.25 is negative, which means I am moving to your left. Yeah. But the acceleration is coming this way, so it's causing me to slow down. Okay? Then, from 1.25 to 5, I'm going to the right, and it's like I have someone pushing me from behind, speeding me up. Okay? So if you're asked whether a particle is speeding up or slowing down, you need to look at the sign of the velocity and the acceleration in that interval. So, speeding up, when V and A are both positive or both negative. Slowing down, V is positive, A is negative, or V is negative, A is positive. So our interval for speeding up was 1.255, and my slowing down was 0 to 1.25. Okay? Questions on that? Okay, finding position from displacement. So before we look at this example, let's get some notes down about displacement and total distance traveled. Okay, so again, let's think about what these mean. Can someone describe the difference between displacement and total distance traveled?
Displacement start to finish.
So comparing where you begin to where you end. Yep, okay. And total distance? We count everything, right? All right, so I think of it as, again, if I'm standing here, if I go 5 feet to my right and 5 feet back, my displacement is 0 because I'm ending up exactly where I started. But my total distance, 10. Okay, so that's the difference between those. So in calculus, we can find displacement with a definite interval of what? Displacement would be, it is, so if we want to think, let me write it. Let's think about final position. Quiet, please. Final position. To figure that out, we need to think about where we're starting, our initial position, plus my change in position, right? Okay? And to get that change, in calculus, it is the integral. So if I am interested in the position at time 1, equals 1. I want to take my position at time 0 plus my change in position. And that would be the integral from 0 to 1. How would I get position from my function in example 1? what was velocity? What's the area under a velocity curve? Distance. So to get S of 1, we want to take our initial position, S of 0, plus the integral from 0 to 1 of d of t dt. So a little reminder over here. If I have a velocity curve versus time, area under that curve, if I were finding area of this little trapezoid, sum up all my trapezoids, velocity is something like meters per second, time is seconds. It would be meters per second times seconds, or meters. So
on the left, I'll probably do.
meters per second, yeah, sorry. Meters per second, there. Okay? So, take a minute and you can do this with your calculator, just so we get good notes in and we don't go short on time. Our function in example 1 was t squared minus 8 over t plus 1 squared dt. And our S of 0, they told us is 9. So to get S of 1, the position and time 1. Right now, on your calculator, do the please.
What is that S of 1 integral of 10? Yeah.
Where? Here?
Yes, right.
This is S of 0.
Oh, S of 0.
Yeah. Yes, same function as example 1. And you don't have to do this. This is one that we could do by hand, but let's just do it on the calculator with F and F. Tell me what we get for our S of 1. I should hear buttons pressing all over the room. Remember to add our 9. Be careful with your parentheses around your t plus 1 squared. What do you think? Well, that would be for S of 5. Did you do 5 seconds?
Oh.
That's the second one. That's the right answer. 5 1/3. 15 thirds is correct. Okay? All right, and then, if we wanted to find S of 5, we could again do 9 plus the integral from where to where? 0 to 5. Of that same function dt. And if Kyle already did this one, we get 44. All right, can somebody give me another integral equation to set up to find S of 5? Based on the information we've already found. I can go from 1 to 5, right? I could say S of 5 is equal to not 9, but 16 thirds plus the integral from 1 to 5. You have a starting point and then just the net change from that starting point to where you're going. Okay? All right. So, questions on this one?
So you can just put in FNN and then Y1 and then
Yeah.
that's all it is you put in and it shouldn't say argument or anything?
No, it should say argument, that's all you put in. So you should have FNX Y1, comma, X, comma, 0, comma, 5.
And
So
then
it is
you can do 1, okay, so 1 or 5.
1 or 5, yeah. So it is the integral of the function. The next argument is X because it's with respect to X, from a number to a number.
Thank you.
Okay?
So are there any, like, are we, so we're just defining displacement X,
This is finding final position.
final position?
So the displacement
finding-
is the integral that we found right here.
Okay.
That is
so
the displacement from where I started. Okay?
Are there
So-
any of them where we just take like the absolute value of it?
So, Let's take a look at our next example. In here, well, so what we did is we took an initial position plus the net change to find our final position. Well, another way that we could do this is we could just find the position function, right? We could integrate and find the actual function for position and then plug in the value at time 5 or time 1. So that's what I want you to do now. I want you to separate the variables and use the initial value to solve for the particular solution of that differential equation on your paper right now. So we'll have ds equals t squared minus 8 over t plus 1 squared dt. And then we'll integrate both sides. So, right now, on your paper, do that. Yes. It is, so what we did here is we said, okay, I have an initial position, plus this second integral is the net change in position. It is potentially ending up doing the exact same thing, but now we're finding a function that we can just plug in to the function. Okay? So, I'm going to get an f of t equals some function here, and I'm just going to plug in 1. Okay? Yes. This is all. Good to get over. Yeah. All right, so right now, let's finish this. We get s on the left. We get s on the left, and on the right we get what? T cubed over 3. And then, this would require a u substitution, technically. And we get 8 times the integral of 1 over what? U squared du, which is 8 u to the negative 1 over negative 1, which is 8 times u plus 1 to the negative 1 over negative 1. So over here, I'm going to write it as plus 8 over t plus 1. Okay, I have noticed on my grading of the test, some people forgot to get all the way back to the initial variable. They got to this point and forgot to go back to the x and the t, so please be careful about that. And what do I need after this? I need a plus b. Then they told me s of 0 equals 9, and I can solve for my c. And we get c equal to what? So my function, s of t, is t cubed over 3 plus 8 over t plus 1 plus 1. Yeah.
We could have just, that part where we did like s of 1 with the integral from this to this, we could have just started with this one.
Yeah, another way to do it. Yeah. So in this case, now I have a function and I can just say, all right, well, if I want s of 1, I just plug 1 into the function. And s of 5 into the function. And we get the exact same answers. Okay? 2 different ways to do the same problem. Most useful, I would say, is the first way, because net change is very prevalent in a lot of questions. All right, are we okay with this one? See you writing? No? All right, let's take a look. Okay, so now, Kyle kind of led us to total distance. So displacement is the integral of our velocity over some interval. And velocity has a sign, positive or negative. And it is important that we have that sign to calculate the displacement. So, total distance would be the integral from A to B of speed. And how is speed related to velocity?
Absolute value.
Absolute value. So to find total distance from A to B, we would integrate the absolute value of V and C. All right, so if we have to do that on our calculator, no big deal. We map now ADS around the function that we are integrating. But if we have to do it by hand, we have to think a little bit. So by calculator, we can just do our FNN of the absolute value of y1 on x from 1 to whatever. Okay? We can set up something like that, right? Absolute value around my function. But when we do it by hand, the absolute value always makes us nervous in calculus because we have to do something about it. There is no rule for dealing with an absolute value. So this velocity function that we had in example 1, started down here, came up like that. Well, if I want total distance, it's the area under the curve of this graph. Well, the area under the curve from 0 to 1.25 is below the x-axis, right? But I don't want to count that as a negative. If I did that integral, I would get a negative value. Okay? So, to do it by hand, you need to remember to find your zeros first. And then set up multiple integrals. Set up multiple integrals. So in this case, we would set up an integral from 0 to 1.25. Of the negative integral of v of t dt. Essentially what I'm doing is I'm reflecting what I have below to be above. Kind of like that. Calculate that area as a positive. Okay? Plus the integral from where to where? 1.25 to 5. And I don't need an absolute value because it's already positive. V of t dt. So this is the trick with all absolute values, derivatives and integrals. You need to think about where this function has 0 and what's going on to the left and right. Yes? All right. Okay. Yeah. So find the total distance from it. We can use your calculator to do it. We are doing the integral from 0 to 5. The absolute value of that t squared minus 8 over t plus 1 squared shush dc. So find that for me. And this you can just go on your calculator. We should be getting very quick with this FNN. That's 42.586. And then if we had broken it up this way, we would get the same answer. Okay? Questions on number 2?
So you should say ABS around the whole thing?
Yeah, so I tend to always put my function in y1,
Yeah.
and then when I do my f and int, I do math non ADS, and then y1. So I don't have to type that whole thing again.
You didn't do plus 9 instead of 0.
This one is not we are not looking for a final position. We're looking for the total distance traveled, so we don't need to add that in. That's a great question. So for total distance, we don't need to start with an initial position. All right, moving on. Okay, let's look at this one. The modeling effects of acceleration. A car is moving with an initial velocity, we'll call v to 0, equal to 5. And it accelerates at a rate of AST 2.4t miles per hour per second for 8 seconds. How fast is the car going when the 8 seconds are up? What am I looking for? I'm looking for velocity at time 8. So here is our initial position and final position type of problem. So if I want v of 8, then I want to take my v of 0 plus the net change. Which would be the integral from 0 to 8 of what? I would change in velocity. The integral of the acceleration. So we get, what, 1.2t squared from 0 to 8. So 5 plus 1.2 times 4. 1.2 times 0. What do we get? Yes, okay. So 81.8. And this is a velocity, so it is miles per hour in this case. So again, that initial value plus the net change, what we're going to get with it.
Out of the physics equation,
They're not helpful.
okay.
Nope. Unless I say so in a problem, but definitely not. All right. So the next thing we are at, if I can get back up there, is how far does the car travel? What am I looking for? Total distance. All right, so we have some work to do. We know total distance is the integral of the absolute value of the velocity function. Do we have the velocity function? We have the acceleration function. So can I get to velocity?
Yeah.
All right, how do we do that?
1 point.
Integral of AST dt. So that's going to be integral of 2.4t.
1.2t squared plus 3.
Okay, to you. And we get our 1.2t squared plus c. But I need to solve for my c. So v of t equals 1.2t squared plus c. And v of 0 equals what? 5. Yep. So we're going to plug 5 in here, equals 0 plus c, so our c equals 5. So my velocity function is 1.2, oh, that's okay. You're ahead of me. Finish 1.2t squared plus 5. All right, but I need total distance, so what do I do now? I'll do the integral of the absolute value of 1.2t squared plus 5 dt. Do I need the absolute value this time? That thing is always positive in our interval from where to where? 0 to 8. And we'll get it.
Can you go over real quick again how you get rid of the absolute value if it's not?
Yeah,
positive
so,
like that?
in this case, we wouldn't have to do anything because this function is a parabola that shifted up 5. So it is above the x-axis on our whole interval from 0 to 8. The area under the curve is all positive. You see that? Okay. So if we had a case where, I don't know, it went like this, and I want total distance traveled, I want to count this distance right here as a positive. So let's say I was going
Oh,
from,
yeah, I remember.
you with me?
Yeah.
A, let's call that A, let's call this B, and this B. So I would do the integral from A to B minus the integral from B to C to make that a positive value,
Okay.
plus the integral from B to whatever.
Okay.
Okay?
You specify the zeros.
Yes, honey.
So there's multiple ways to cross it, you use multiple.
Yep. If there were 5 zeros and you cross the x-axis each time, then you would have 5 intervals for that. Okay. All right, very good question. What do we get? Does someone get a sign? 244.8 is right. And this is a weird distance, but it is miles per hour times second. It is a distance. We could alter it to be a mile, but we don't have to, or some portion of a mile. All right. Let's see what's next. We don't need to do this data. This one, I'll just talk about this one quickly. So a lot of times, and you saw this on your, you're given data instead of functions. And actually, in real life, very few times do they come up to you in your job and say, well, here's the function, the model is exactly what we need. This doesn't happen. You get a lot of data. And you can make a model, or you can use the data to come up with information. So here we have a table of data finding gallons pumped from rate data. It says a pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. The rate is in gallons per minute at which the pump operates is recorded at 5-minute intervals for 1 hour. How many gallons were pumped? What are we doing? I want you to think about a picture first. That's a straight line. I'll do that. All right. When we think about the picture, at time 0, we're at 58. This is the kind of thing I really want you to start drawing because it just makes it easier to see things. At time 5, we're at 60. At time 10, we are at 65. And so on. So, oh Lord, help me with the straight line. I know I can just pull that thing out. Oh boy. There it is. There we go. So, you can see the trapezoids that we can build to approximate the area under this curve. Here we have, on the y-axis, we have gallons per minute, and on the x-axis, we have minutes. I always use the units to help me find my units that I'm looking for in the end. So if I'm finding the area of this trapezoid right there, I'm doing gallons per minute times minutes to give me gallons. What am I asked to find in this problem? How many gallons were pumped? So that helps me realize that to do this, I need the area under the curve of this data. Well, I don't have a function, so what do I have to use?
Trapezoidal.
Thank you, sir. Trapezoidal. We have a 1/2. And what's the height of every trapezoid? 5. What if they were all different widths? Like something you may have seen at some point in your life. You gotta do them individual. Find your trapezoids individually. All right, so here we would have, since they're all the same width, we have 1/2 times 5 times 58 plus 2 times 60 plus blah, blah, blah. It's 2 times 63 plus the last one. Anyone see it? 65? No, 63? Yeah. Okay. And there's our trapezoidal. Done. And so we could plug that in, but let me just tell you, this is from your book, so it's in there too. 35 something. 3582.5. Gallons. Don't forget your units. All right. And I'm rushing through that one so I can get to the word problems because we will be using calculus to help us find work and force sideways. So we need to remind ourselves about a few things. So in this problem, it said to take the force 10 newtons, stretch a spring 2 meters beyond its natural length. When we talk about springs and force, we need to think about Hooke's law, which is force equals some constant times the displacement. X is the displacement, F is the force. And then it says how much work is done in stretching the spring over 4 meters. So work is what? Force times distance. Force times distance. All right. So when we are calculating work using calculus, we are going to be integrating a whole bunch of force times distances over a certain long version. Okay? So in this one, we need to get a function for our force to begin with. So what is the force that they give us? 10 newtons, and the displacement is 2 meters. So we can solve for our k, where we get 10 equals k times 2, and our k is 5. So my function for the spring is f equals 5x. And then to calculate the work, we want to set up like this. What you want to think about is making it a 3-month sum problem, where we're finding the area of a bunch of rectangles, force times distance, where force is our function, 5x. That's going to be the height of each of our rectangles, and what's the width of each of our rectangles? That's, when we sum them all up, we'll get 4 meters. But when we make a 3-month sum, we have something like this, what's the width of each of these? What do we call that? We call it dx, differential in dx. Tiny, tiny, tiny little width. So the force times the distance would be 5x times dx. And we want to sum all of those up over our interval of 0 to 4 meters to get our work. Okay, so we get 5 what? X squared over 2, very good. We evaluated between 0 and 4. And we get 40, and what are the units for work? Joules or newton meters? Foot-pound is the English unit for that. All right, and that is the end. Now, take out your assignment sheet. I did this assignment last night, so I know what to take off. Take off number 6. 2 and 4 have 3 parts each. This is the same type of problem. 2 of those. And take off number 37. Otherwise, it's a pretty manageable assignment. And you have some time. Do not waste this time. Get started now. You have some time.
Oh, no.
Go ahead. Get 3 or 4 problems done.
So from, first I was talking about
Oh, we got one. So, if you're doing you've got the area under the curve
or maybe it's an H problem.
So that's coming out all of it, right? And then divided by the number of
But what would it, without 1/10, what would that be?
it would be
Oh, so it'd be like,
yeah, exactly, right, but with temperature, that's not all right, get a few done, folks. Anyone need any old paper stoves? Calc form? Does anyone need another one? Rip from the headlines. Does anyone need that? Due Monday. Okay. Yeah.
So,
I missed a couple things when you moved on the
Oh, yeah.
slides. So here that's the position so we had
This is the velocity.
okay, so we had velocity to start with. Mark that. So this is not dx.
It is DS, they call it, so, the DS dt is equal to V.
Because
DS over V.
yeah, I agree. Okay. So yeah, so
And then we
then
just separated our variables so we can integrate
good. And then we find this is the position.
position.
So to get from velocity to position, you do the integral. So now we have position, and then we did all this stuff, so we found it. And then at position 0, it's 9.
So,
At the 0
see,
equals
we've already
9.
taken that, they called us S of 0 equals 9. And we use that to help us solve for our
Because then we can plug in 0 for all the t's, and we know the
9 for the other.
Okay, and so then what do we do? What are we trying to find?
So then we went back and we found what we had found in problem number 1, S of 1 and S of 5.
Yeah,
So
cool.
now, since I have an S function, all I need to do is plug in 1 here. That's 1 cubed over 3 plus 3 over 2.
8 over
2 plus 1.
Okay.
So it's another way.
Another way to find. Okay.
Whereas over here, we did it as initial position plus the net change.
Initial position plus net change.
The integral from 0 to 1 is secondary net change. How far it's from where it is. Okay. And then here we did the same thing. We did sine cube over 3 plus h over 6
Yeah.
plus 1 and we got 1. So 2 different ways to do things.
Cool.
Okay, move on to the next.
I don't know if this is correct or not for the first question.
The first one.
How fast this shadow is moving.
Oh, yeah, okay. So you did, where's your X and your
So
Y?
I did X over Y S.
That's what I did.
And then for this one, I set it up this way, but I got a positive answer.
And what are we finding? X
The
axis
rate of
integral.
change between,
And between the tightrope and the harness. So it's this one, right?
Yeah.
Okay. And it looks like it's just getting smaller. I think what you want to do here, let me think about this. Yeah, you're gonna need to.
Yeah, read, what? No. These gonna be the.
Yeah.
Love these stuff in games so much, right?
product rule.
How they looking?
I do well.
What JV had to do is we just had to watch fossil ranges off and then run it the whole time.
There. Oh, really?
This is
CYDC, is it CYDC?
But did you,
Yeah.
would you be able to
Where's our Y
take
again?
mission every shot, like?
Yeah, exactly. And, except your X and your Y.
Yes.
And then they'll
Is what?
positive 1.5.
Walking forward, that distance is getting.
Well, the distance between here and here would be getting
Right,
smaller.
here and here is getting large.
That should still work.
Yeah, yeah.
Yeah, like these guys.
But as soon as this goes away, there's nothing to make it negative.
We went to outside from
So I'll try and solve your way.
Or if
And it seems like,
from 0 to 1.
I don't see anything wrong with your method, I think I may have.
Oh, so it'll be like.
Oh, yeah. Oh.
No, they do that.
Yeah.
That one is done.
And then they have like
That
Why?
one is
a couple of
Yeah.
This is so hard to plug in because it's so low. I think we contribute again more out of our.
Yep.
They're more close to this.
And that jersey itself, probably.
Let me find
Yeah, that's how, Morton Holland.
So you did X 75.
Yeah, Morton Holland's back, and he's like, yeah, and then you can just go whatever school, like, all the baseball players.
Yeah, and just remember which ones are not changing.
The one thing I can remember was like, you want to do input different, like this, you do something different, why does it work?
Well, you need to make sure, what you need to remember is that
But baseball
Yes.
is
This work differentiating the ability and looking at the activity when it's
What are you trying to do, why?
I think it looks okay.
Yeah, I was gonna ask you.
All right, Kyle.
Yeah, that's on your deck.
Bye, bye.
Up there.
It can come from anywhere. So most likely it's not from what we're doing right Bye, sweetie. Bye, Kendall. Bye. Have a good day. You too. Thanks.
Bye,
Bye, Kyle.
Oh, that's not important.
Oh, geez.
I think you're good. Yeah, I'm killing it.
Oh, my clothing. Put it all back on. I'm coming. I'm leaving.
Hello, look at you.
We gotta get dressed.
You know, I gotta tell my brother, he's a software designer. He has to invent the workspace app for a tablet. And he goes, oh, you're stupid, because he's my big brother. And he's like, oh, you're stupid. No, you don't know
What?
anything. And no, but he could do that. That's what he does for a living. He writes educational. But he could design something like that for it, and he writes it for Android. You should tell your husband.
She wanted something else to happen in this period, and I'm like, I'm sorry. Okay, no, sorry. I got undressed. Hello, Hannah. How are you? I'm good. So you have a test to take, yeah? Oh, and then... Oh, okay. Here you go. All right. We've got assignment sheets for the next chapter. Let me get it. All right, so Daniel, when we your homework, chat with me about. All right, any other calc forms? I am up to 27. Oh, really?
You get back to it.
Is there a binder left?
Are you kidding me? Oh my God.
There's going to be a big moral conflict that I don't think is ever real conflict.
Yeah.
Fourth one of these during the time.
It means that the land is going to be very exciting to see.
So good. 10 times better than mine.
30 after there. All right, good. 31. We're at 31. Very good. Awesome, right? Okay, so let's talk. Who needs to take a test still in here? Have we discussed? Remind me. Wednesday, Wednesday, 2 time. And, okay, so step outside. Emmy and Hannah, step outside. I have a couple things to discuss. So if you could move it.
I'll remember to bring back.
Good, thank you. Sorry. And just move that door back into it. All right. So just to give you a heads up, so the first half of the tests are graded, and they don't look bad. They don't say. I am going to be grading. There are 110 cards available, and I'm going to be grading it out of 100.
Word.
So the limit problem didn't cost. Although you had a calculator, so with that limit problem, my approach would have been find the function, actually skip down to C, find the function, come back up, put that in my calculator, and then just zoom in around that number, right? We have a calculator, limits is just what's happening as I'm approaching, okay? Technically, the only other way is with L'Hopital, which you guys don't know do yet. So I thought I'd leave it on there and see what happens. It wasn't that pretty what happened. So, I don't remember it. I have people who said to me. So, I can't say it. If I did remember. I do remember. All right. So, it'll be graded out of 100. So there's some curve built in. Okay? But you should be aware, I know it was a hard test. I know that you're pressed for time. And those are things that we have to focus on this semester, because the AP test is long, and you want to get as much done as you can. You need to start working quickly and efficiently. So we're going to do that. And we need to know what to do with a test that really, really pushes us. Okay? So it's good that it did that. Now, grade-wise, people panic about grading. All right. So a B in this class is an excellent grade. Can we please remember that? A C in this class is a very respectable grade. Okay? A D in this class shouldn't happen. There's no reason it should happen. Okay? But a C might happen. An A in this class, rejoice. Wonderful. Okay? But it's a very challenging class. It's your hardest math class. So just be ready for grades to be a little lower than you're used to. It's okay. All right? You still get a bump in this class anyway, so you'll be all right. All right. Now, do I get A's, B's, and C's? Yes, I do. I get plenty of A's, I get plenty of B's, I get plenty of C's. Okay, B's are rare. You have to work really hard to not do a lot of things to get a B. Okay? So this should not happen. All right? So I just wanted to touch base to make sure we don't have any panic going on. You don't know what you got on this test yet. I don't know what you got on this test yet. But don't panic. Also, if at any time you take a test, and it is, you know, you usually get a 78 to an 87 in this class, and you do it at 37. then yes, you should come and we should talk about what happened and what we could do to make a change, you know, to allow you to bring your grade back up a little bit. I don't do that for Steve, okay? I think if he is a respectable grade in there, as I said. But if you totally blow something, or something happens so you couldn't perform the way you usually do, you should absolutely come and see me. The worst case scenario is that I say no, and that does not mean I hate you. That just means I'm saying no, and we're moving on, okay? So it's no big deal. But if you bottom out on one, come and talk to me, and we'll find something to help you raise that grade back up. Okay. All right. Come on, I remember taking. Okay. So we start chapter 8. Please look at your assignment sheet. Take a look at the page where we have quizzes, please, or I should say quiz, and tests. We're having a quiz on day 2.3. Should be February 3rd, I don't know why it says 2.3. But notice it is a 2-problem partner quiz. That means it's short. Listen up. It's short, and you work with somebody else. I will also be teaching that day, so when I mean it's short, I mean I'm stopping you. Okay? You'll get a certain amount of time, that's it. Okay? So work well on that. So make sure you're doing your homework up to that point. And your test is on February 12th and 13th. Okay, if you're not going to be here for that day, you need to let me know ahead of time. Anything else? I was able to build in a couple of areas where we get to have a little more fun other than being just talking. A little bit. So that's kind of nice. But today, I'm talking. So take out your notes. We start chapter 8 today.